Good morning, everyone. My name is Bina Nusantara, and today I'll be presenting Fenit, a mobile application for automatic chessboard digitization and FEN generation using computer vision. This is joint work with Vincent Oy, Theodenata Harjanto, and Bhakti Amirul Jaber from Bina Nusantara University. Chess today is heavily supported by digital engine, but most games are still play over the board. To use an engine for analysis, someone has to convert the physical position into Forsyth-Edwards Notation, or FEN, which is the standard text format engine understands. Doing this by hand takes time and it's easy to make mistakes, especially in a messy middle game position with a lot of pieces on the board. That game between the physical board and the digital tool is really what motivated this whole project. Looking at firework, there's been a real progress, but also consistent limitation. Giselsky et al. Used a heatmap-based lattice point detector and get around 95% accuracy, but it needed a fixed camera perspective. Wolfen and Evangelovic got close to 99% with an 8x8 grid-based deep learning, but it was trained almost entirely on synthetic data, so it struggled outside controller conditions. Mehta built an AR-based assistant with about 93.45% accuracy, but again, it needed a stable fixed camera setup. Menezes and Maya used YOLO-V4 and reached 89% precision, but only from strict overhead angle. So across all of this, the common thread is that none of them turned into a complete mobile app that could take an unconstrained real-world photo and output a valid fan string. That's the gap that we want to close. Fenit is built around a three-stage pipeline. The first stage covers architecture and data preparation. The second is board normalization, and the third is fan transcription. The whole thing runs as a client-server application, where the phone just handles capturing the image, and the server does all the heavy inference work. On the front end, we use Flutter and Dart, so the same code base run on both Android and iOS. The backend runs on Python with FastAPI and UVCon. When a photo is taken, it gets sent from the phone to the server over HTTP using multipath form data, which is more bandwidth efficient than sending a base64 encoded image. On the server side, we run Inference using a authoritative YOLO-V8 combined with OpenCV, and the result comes back as JSON response containing the fan string. Because all the processing happens server-side, performance stays consistent no matter what phone someone is using. For training data, we collected 419 natural smartphone photos of chessboard and annotated them manually using CV80. We split this 85-15 into training and validation, giving us 417 training images and 73 for validation image. To make the model more robust, its training image was augmented into 3 synthetic variants, using things like random rotation, perspective shift, color jitter, Gaussian blur, and cause dropout to simulate occlusion. That brought our total training pool up to 1,668 images. We train using YOLO-V8 large force with ADMW optimizer a learning rate of 0.000345 at 640 by 640 resolutions for 50 epochs. Once a photo comes in YOLO-V8 detect both the piece bounding box and the four board corner key point at the same time. If the board detection confidence is low, the system fallbacks to drawing a convex wall around the detected piece to estimate where the corners are. We then expand those detected corners by 8% so that tall pieces sitting near the edge don't get cropped during the warping. From there, a homography matrix flattens the angle photo into normalized 500 by 500 grayscale grid. That grid gets divided into 64 uniform cells through geometric interpolation, and each piece is assigned to a cell based on its centroid. The trickiest part here is figuring out orientation. A top-down chessboard is symmetric, so there's nothing in the image around that tells you which side is what. Fenit handled this by testing of 4 possible rotations, from 0, 90, 180, and 270 degrees, scoring each one with a heuristic. That heuristic reward pawns moving in the correct direction, penalize pawns sitting on illegal back ranks, and check that the king are roughly where they should be. Whichever rotation scored highest is treated as the correct one, and the grid gets serialized row by row into a varied FEN string. Overall, the full pipeline achieved a 70.49% perfect FEN extraction rate across 61 validation images. On the detection side, we got 96.47% MAP50 for bounding box and 95.18% for post key points. On completely empty blocks, the geometric pipeline hit 100% accuracy, which tells us the spatial mapping itself doesn't introduce compounding errors. And end-to-end, the whole pipeline averaged about 621 milliseconds per image on an RTX 4070 Super, which is fast enough for real practical use. When we compare against the firework at an IOU threshold of 0.5, our model's 96.47% MAP50 comes out ahead of 4 studies shown here. Dink's HOG-based system reached 95%. Chiselsky lattice point method also reached 95%. Mehta AR-based system reached 93.45%. Menezes and Maya YOLO-V4 approach reached 89%. On top of the detection number, our system is the one that actually produced a complete FEN string, not just a raw detection. We had 15 participants, a mix of novice and experienced chess players, test the app using the system usability scale, and get the average score came out 82.5 out of 100, which falls into the excellent category. On the error side, about 29.51% of FEN extraction weren't perfect. The two main causes were pieces that looks visually similar from overhead, like the queen and bishop, getting confused with each other, and heavy occlusion, where the tall pieces clustered together extend past their grid cell boundaries. So, to wrap up, Fenit shows that pairing a strong object detection model with a strict geometric mapping approach gives you a system that both robust and genuinely usable. The 70.49% perfect FEN rate and the 82.5 system usability score back that up. And they tell us this combination of neural detection and rigid geometry is a solid foundation to build on. Looking ahead, we want to add temporal frame analysis, so the system can use a Lego move constraint across consecutive frames to catch the errors. We also want to expand the training set with a synthetic 3D environment to cut down on the piece misclassification issue that we see from top-down angles, particularly between pieces like the queen and bishop. Overall, we believe Fenit takes a real step toward closing the gap between physical chess and digital analysis. We hope this work serves as a useful foundation for future research in mobile-based chessboard digitization. I want to thank to Vincent, Theo, and Bhakti for their work on this project, and thank you to all of you for giving your time and attention. I would be happy to take any question you might have.